In this video, what we are going to do is continue our journey into the world of carbohydrates, important molecules in the field of chemical biology, by looking at some of the ways to classify monosaccharides. Remember that monosaccharides are the building blocks of carbohydrates, much like amino acids are the building blocks of proteins. As we start to think about how we can go about classifying monosaccharides, we can look at the whiteboard here, which I'm going to bring up, to start thinking about the three main ways that we will classify monosaccharides. And I should add here, when we're talking about monosaccharides, remember that there are two ways that those can appear. They can appear as the open chain form, the linear acyclic form, in other words, or alternatively, those structures can cyclize, they can form rings. And so what we're focusing on here when we look at classification of monosaccharides is we're basing this discussion on the open chain, the linear form of the monosaccharide, that building block unit. Now, remember, as we get started, that when we talk about a monosaccharide, the open chain monosaccharide has a specific formula that it follows. That formula is CnH2n O N. So the number of carbon atoms in the molecule we can use to directly determine how many hydrogens and oxygens there will be in that open chain monosaccharide. So one way of classifying these molecules is by the number of carbon atoms that are present. And based on the number of carbon atoms, which is generally between 3 and 7 carbons, most typically, and they can arrange into a variety of structures to make a huge array of different monosaccharides. Those 3 to 7 carbons, classified based on number, are referred to as trioses, tetroses, pentoses, hexoses, and heptoses, with the common theme being that they each have the OSE suffix to indicate that the structure is a saccharide, a sugar molecule. And the term monosaccharide referring to one sugar unit. So the OSE suffix is a way that you can quickly look at the name of a structure and deduce that it is a sugar unit of some sort. Specifically, when we're classifying and categorizing monosaccharides based on the number of carbon atoms that they have, if it has 3 carbons, it'd be referred to as a triose. And you should be able to, if I ask you on an exam or somewhere else you see the term triose, you should be able to say to yourself, I know what the molecular formula of a triose has to be, because we know that it has 3 carbon atoms due to that tri word. And then we know that these open chain monosaccharides follow this formula that I'm highlighting here with a laser pointer. So we can fill in then, if we have 3 carbons, that we absolutely have to have 2 times n hydrogens. So if there's 3 carbons, 2 times n is 2 times 3, which is 6. And then the number of oxygens is equal to the number of carbons, so that gets filled in with 3. Tetros refers to 4 carbons, so it'd be C4H8O4. Pentoses are really common. We're going to see that the building blocks of nucleic acids incorporate some pentose units, and that's going to be C5H10O5. Hexoses are super common. An example of that is glucose. C6H12O6 is the formula that you would see there. And then heptose refers to 7 carbon atoms, and that's going to be C7H14O7 there. So that's going to be one way that we can go about classifying structures, is based on the number of carbon atoms that they have. We can also classify them based on the functional group. The open chains of these functional groups generally have either an aldehyde group or a ketone group present in them. And so if the open chain form has an aldehyde group, we refer to the structure as an aldose to classify it. If it has a ketone functional group in the open chain, we refer to it as a ketose. So classifying based on functional group, we really can break it into 2 categories for these open chain monosaccharides. Aldose, and again, the OSE there is your clue that this is a carbohydrate building block. And the ald there stands for aldehyde. So an aldose has an aldehyde group in the open chain. a ketose, the KET there of ketose, refers to there being a ketone group in the open chain. And so, for example, we could take a look at, let's say, D-glucose. I'll draw the structure of D-glucose here. And we can think about the structure of D-glucose and classify it based on these criteria about number of carbon atoms and functional group. So I'm just drawing out the structure of D-glucose. You don't have to memorize this structure, but you should be able to interpret it and classify it based on the information that we've provided here. So this is the structure of D-glucose. So what I want you to do is take a second and ask yourself what this would be classified as based on the number of carbons and based on the functional group. So based on the number of carbons, we see a grand total of 6 carbons, 1, 2, 3, 4, 5, 6 in D-glucose. So one designation that would be correct for this is we could classify D-glucose as a hexose. And additionally then, based on functional group, aldehyde and ketone are the 2 possible choices. The CHO group is our aldehyde functional group, a carbonyl group directly bonded to a hydrogen, in other words. And so this is going to be classified additionally as an aldose. And sometimes you will see these 2 terms merged to refer to the structure as an aldohexose. So the hex part is referring to the 6 carbons. OSE refers to the fact that it is a saccharide, a sugar molecule, and aldo refers to the aldehyde functional group. So let's do a different example. We'll look at the structure of D-fructose. In the structure of D-fructose, we'll go ahead and draw that out here. In its open chain form, we'll get into alternative closed chain or cyclic form of these in our next unit here. But for now, we're focusing on the open chain structures. And the intersections of these lines, where the lines cross and form a T, that intersection represents a carbon, of course, like a line angle formula type structure would do. So this is our structure of D-fructose. And in the structure of D-fructose, we can ask how we would classify that based on number of carbon atoms. So to classify based on number of carbon atoms, count the number of carbon atoms. It turns out to be 6. So this, like glucose, would be classified as a hexose. And then the other classification that we've talked about so far is based on whether it has an aldehyde functional group in the open chain or a ketone functional group. In the case of this, you will notice as a key structural component here, we have a carbonyl group directly bonded to 2 carbon atoms. Carbonyl directly bonded to 2 carbon atoms, definitely a ketone functional group. And so we refer to as a ketose. And merging those 2 terms together, similar to what we did for glucose, you refer to this as a ketohexose. 6 carbon atoms leading to the term hex, keto referring to the fact that it's a ketone functional group. So that's a second way to go about classifying these molecules, is based on what functional group the monosaccharide has. The third way that we can classify these is based on the chirality of that monosaccharide unit, the stereochemistry of it, in other words. And when we talk about the chirality of these structures, we generally refer to carbohydrate monosaccharide units as presenting with either the D configuration, and we refer to those as D sugars, versus the L sugar. Now, the sugars that occur naturally are most commonly composed of D configuration monosaccharide units. So that's why it's no coincidence that we used as our examples here D-glucose and D-fructose. Those are the most commonly encountered stereochemistries, the D configuration. So when we're looking at sugars and we say that a sugar is a D sugar, like D-glucose or D-fructose, what are we referring to there? Because as we look at the sugar molecule, we see that we have multiple chiral centers within each of these sugar molecules. So D-glucose has a chiral center here, highlighted by the laser pointer, coming down here, 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 because of the fact that each of those carbons has 4 different groups bonded to it. Fructose is a similar situation where there are multiple chiral centers. So the way that we assign and describe the molecule as being a D sugar or an L sugar is based on the so-called penultimate carbon atom, the next to the last carbon of the chain. So the carbon atom that's right here and the carbon atom that's right here is the penultimate carbon atom. Almost at the end of the chain, next to last is what we refer to as the penultimate chain or the penultimate carbon. And so we're referring specifically when we talk about a D sugar or an L sugar to the configuration of that particular carbon. And what is going to be the case is if in our projection here, the hydroxy group is on the right, we refer to that as a D sugar. If the hydroxy group at that penultimate carbon atom is on the left, we refer to it as an L sugar. So D-glucose, D-fructose, we look to the next to the last carbon out of the chain. We see the hydroxy group is to the right, like I'm highlighting here and here in glucose and fructose. Seeing that that's to the right, that indicates that it is a D configuration sugar. And most of the natural carbohydrates are going to contain exclusively D configuration sugars rather than the L configuration monosaccharide units. That is definitely in contrast to the proteins that we were talking about, where L amino acids were the building blocks of proteins typically. Here it's D monosaccharides as the building blocks of carbohydrate molecules. Now, as we think about this chirality, one thing that can come to play is that we can refer to, when thinking about the chirality, we can think about the relationships between different sugar molecules. Sugar molecules that are related as enantiomers will have the stereochemistry inverted at every single chiral center. Stereochemistry inversion at not all of the chiral centers, but some, will result in the sugars being related as diastereomers. So for example, if we were looking at 2 sugars that are diastereomers, an example would be if we took D-galactose which I will draw out, sketch out the structure of here. It is aldohexose, much like glucose is also an aldohexose with 6 carbon atoms and an aldehyde group there. It's a D sugar, so that tells you straight away that that hydroxy group that's at the next to the last position better be on the right. Coming up the chain here, filling in my hydroxy groups and hydrogens all along the way to give me that CnH2n ON formula, gives us this structure. And if we relate that structure to the structure of glucose, and I will draw the structure of D-glucose here. I'm going to abbreviate that as D-glu for glucose. We have our aldehyde group, grand total of 6 carbons in the chain is what we're going to end up with here. And in D-glucose, hydroxy group here, 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 and here. Again, you don't need to memorize these structures, but you should be able to deduce the relationships between these compounds if you're given a pair of them. So for example, if we were comparing D-glucose to D-galactose, we would classify these both as aldoses. Both are hexoses. And when we think about the relationship between the two structures are related as diastereomers. Remember the diastereomer from your organic chemistry terminology or biochemistry terminology means that the configuration, that is the RS or DL configuration, changes at least one chiral carbon or stereocenter, but not all. If it changed at all of the stereocenters, if all changed, then it would be an enantiomer. So here, we haven't changed the configuration of all of the stereocenters. We have a stereocenter that's the same here versus here with a laser pointer. Then we come to the next one, also the same. We come to the next one, different, and we come to that penultimate one, the one that dictates whether this is called a D sugar or an L sugar, and those are the same. So we have some stereocenters that have the same configuration, some that have a different configuration, and that's why we refer to these as diastereomeric sugars. If they were enantiomers, what that would mean is that we would make the mirror image of one sugar to convert to the other, like L-glucose versus D-glucose would have the mirror image of the structure of D-glucose. So rather than this hydroxy group being oriented to the right, as we have it here, in L-glucose, it would be oriented to the left. Next hydroxy group up, rather than being oriented to the right, would be oriented to the left in the enantiomer, and so on and so forth. So all these groups that are to the right would be instead to the left if we were making the enantiomer, if we were converting D-glucose into L-glucose. So with diastereomer sugars, what you will notice is that you haven't changed the configuration of all the stereocenters, but you have changed the configuration of some of them. And the names of the diastereomeric sugars are going to differ. So galactose versus glucose, definitely different parent names there, even though the structures are related as diastereomers. That's one of the nuances of biochemistry, is that many of these structures take rather historic names. So unlike organic chemistry IUPAC names, where you systematically would go through and assign the RS stereochemistry at each of the chiral centers, and then the parent name would be the same for the two structures that are related as diastereomers. When you're dealing with sugars, due to the historic nature of the names, you have things fall in like galactose, glucose, etc. And you have to look at and compare the structures to determine whether they are related as diastereomers, whether they are related as mirror images, meaning enantiomers, or whether they are two totally separate compounds. So with that, we will conclude this unit on ways to go about classifying the monosaccharides. And you should be comfortable with classifying monosaccharides that are open chain form based on the number of carbon atoms, based on the functional group that's present, and based on the chirality. You should be able to compare and contrast and classify different monosaccharides.